Hello everyone, welcome to the second session of the topic Relations and Functions, Class 12. I am Deepa, faculty at Silver Hills Public School, Department of Mathematics. In this session, we will be discussing a special type of relation, that is functions. We all know a relation from a set A to a set B is always a subset of the Cartesian product A cross B. So, what is the difference between a relation and a function? When can you say a relation is a function? Let's see that. So, here is a definition of function. Let A and B be two sets. A relation f from A to B is said to be a function if it satisfies certain conditions. So, what are the conditions? The first condition is every element in the first set, here which is the first set, it is A. Every element in the first set has an image in the second set, that too a unique image. So, what do you mean by unique image? One and only one image. So, if a relation satisfies this condition, we say that relation is a function. So, this is how we denote a function. If a relation f satisfies a condition that every element in the first set has a unique image in the second set, we say f is a function from A to B. And if you have an ordered pair in F, suppose AB belong to F, we write f of A is equal to B. So, here B is called the image of A under F. And what is the name of A? We say A is a pre-image. B is called the image and A is called the pre-image of B. Now, let us see some of the examples. You can see so many arrow diagrams here, and we know arrow diagram is a pictorial representation of relation. So, we have so many relations here. Now, we are going to check which among these are functions and which are not. So, hope the definition is clear to you. So, what was the definition? We concentrate on the first set. So, every element in the first set has a unique image in the second set. So, let us check one by one. First one, I have denoted this relation using F1 and we are going to check whether this relation is a function. Look at the first set, you have 4 members. Every element in the first set has an image, that is from each member an arrow goes to the next set, which is the next set here B. And is the image unique? Yes, 1 goes to A, 2 goes to B, 3 goes to D and 4 goes to C. So, I can conclude this relation is a function because it satisfies all the conditions of a function. Look at the next figure. What about this one? Every element in the first set, it has an image in the second set. And is it unique? Yes, it is unique. Look at here, 1 goes to B, 2 goes to B. So, do not think that is not a function. Why? Because 1 is going only to B, not to any other number. Same way 2 goes only to B, not to any other member on the right side. So, I can conclude the second relation F2 is also a function. Coming to F3, what about this one? Yes, every element in the first set has a unique image in the second set. So, that is also a function. Now, what about F4? Consider the first set. All the members in the first set has a unique image in the second set. So, F4 is also a function. Now, coming to F5. Look at the first set. Look at the element A. Here I can see A goes to 1, that is an arrow comes from A to the member 1. Same way an arrow comes from A to 2. So, that means A goes to 2 members. A has 2 images, which contradicts the fact that F is a function. So, this relation F5 is not a function because every element in the first set does not have a unique image in the second set. Now, one more example is left. What is that? First set, look at the member C. That C does not have an image, and as per our definition, every element in the first set has an image, and that too a unique image. So, an arrow does not go from C to the next set. So, the last two, that is F5 and F6 are not functions, but the remaining members, they are all functions. Now, let us discuss what are the different types of functions. Basically, 3 types are there. First one is called 1-1 function. Another name for 1-1 function is injective. Second one is onto function. Another name for onto function is surjective. And the third one is 1-1 and onto function, and the name for that is bijective. So, we are going to discuss 3 functions: injective function, surjective function and bijective function. So, now let us see what is 1-1 function. 1-1 function, a function f from x to y is defined to be 1-1. 1-1, another name for 1-1 is injective. If, what is written here? If the images of distinct elements of x under f are different. What does that mean? In simple words, you have a function f from x to y. X is a first set and y is a second set. We say f is 1-1 if different distinct elements of the first set goes to distinct members of the second set. In that case, we say the given function is 1-1. And let us see what is the definition. Suppose you take 2 members in the first set. Here it is x1 and x2. F of x1 equal to f of x2 implies x1 equal to x2. That means, if you substitute x1 and x2 in the function and suppose you are getting the same value, then f, the given function, will be 1-1 only if x1 is equal to x2. If x1 and x2 are different, then we will get x1 and x2 goes to a same member. So, that won't be 1-1, we will call it as a many-1 function, many going to 1. So, I will just make it clear to you. Suppose I have 2 sets, x and y. And I am just listing few members here, say A, B, C. I have 1, 2, 3. So, like in our definition it was let x1 comma x2 comes from the first set. So, here I will just take A and B as my x1 and x2. Suppose f, if I name this function as f, suppose A goes to 1 and B goes to 1. Okay. Let this be the relation connecting the members of the first set and the second set. Here I am getting f of A is 1, f of B is also 1. That is, function values are same, A and B goes to the same member. So, can we say this is 1-1? If it is 1-1, 2 arrows will not go to a same member on the other side. That is, if this arrow coincides with the first arrow, that is, only if A equal to B, then I can say this function is 1-1. Okay. So, in simple words, just check whether different members in the first set goes to distinct members in the second set? If yes, we will conclude it is 1 1, or else if many are going to a single number or single member, we will conclude it is many one function, just the opposite of 1 1 function. Now, when we do problems, this concept will be clear to you. So, here I am just giving you an idea of the definition of 1 1 function and how to identify whether a given function is 1 1 or not. Look at this. We have two arrow diagrams here. Two functions are given here. Now, let us check whether the given functions are 1 1 or not. So, look at the first set. 1, 2, 3, 4. There are 4 members, and you can see that all these different members goes to different members. That is, from the first set, 2 arrows going to a single member is not seen here. So, I can conclude this one. This is a 1 1 function. Now, what about this one? See, from the figure itself, it is very clear. See, look at this. From 1 and 2, an arrow goes to A. So, many going to 1. So, I can conclude this is an example for many one function. Many one function, and this is 1 1 function. Okay. So, now the next one. So, 1 1 is over. Another name for 1 1 is injective. Second one is onto function. So, what is onto function? A function f from x to y is said to be onto. Another name is surjective. If every element of y, here the second set is more important. In 1 1 we check the first set, all the members of the first set, whether they are going to different members, we conclude it is 1 1. But when we discuss onto function, second set is more important. What is written here? If every element of y, y means the second set, is the image of some element of x. That is, for each member in the second set, there is an arrow coming from the first set to that set. If so, we will conclude that function is onto. That means every element in the second set will have a pre-image. There won't be even a single member in the second set without a pre-image. In that case, we will conclude the function is onto. One more method is there. How can you conclude a function is onto? Suppose your second set is y. And what do you mean by range of a function? The collection of all images. If every member in the second set has a pre-image, then I can say range will be equal to codomain. So, that is another method to check whether the function is onto. If you are getting range of a function is equal to codomain, then I can conclude that function is onto. So, once again, for every element in the second set, if you can find an x in the first set such that the y is the image of x, then I can conclude the function is onto. One more way of saying is, if the range of the function is equal to the codomain, then also we can conclude the function is onto. I will just give you one example. Say, x, y, and you have a function a, b, c, d, e, f. Okay. So, look at this one function. By looking into the figure, can you tell me whether this function is onto? So, when you see the word onto, where do we check the second set? Look at the second set and we just check whether every element in the second set has a pre-image. So, D has, E has, but what about F? F does not have a pre-image there. So, I can conclude this is not an onto function because F does not have a pre-image. Suppose we have one more member here, say I would take some G, and if an arrow goes to F, then I can conclude this function is onto, because all the members here in the second set has a pre-image. Okay, so all the members in the second set has a pre-image, so the function is onto if I change my relation like that. Now X is called the domain of a function, Y is called the codomain, and what do you mean by range? The collection of all images. Now this function is onto. So when we discuss range, what are the members coming in the range? It is D, E and F. You have set D, E, F. Is that equal to Y? Yes. So if a function is onto, range of that function will be equal to that of the codomain, and it is very clear from this example which I gave you. Now just identify which of these functions are onto. Look at the first one. You have a function here. Just look at the second set, Y. 3 members are there, A, B, C, and that is each member, it is an image of some member in the first set. So this is an onto function. Now what about this one? You have C, a member C in the second set Y, which does not have a pre-image. So we will conclude this is not an onto function. The first one is an onto function. Now the third one, 1, 1 and onto. What is another name for that? We call it as bijective function. So 1, 1 and onto. So from the word itself it's clear, a function which is both 1, 1 and onto is called a bijective function, and you know the condition of 1, 1, you know the condition of onto also. If a function satisfies both these, we will conclude the given function is bijective, and here is an example for that. You have a function, I named it as F5. X has 3 members, Y also has 3 members. So we are going to check whether it is bijective. So that means it has to satisfy 2 conditions, 1, 1 and onto. So when it is 1, 1, it's a first set. Different members goes to different members. So it is 1, 1. Coming to onto. Concentrate on the second set. Every element in the second set has a pre-image. So this function is 1, 1 and onto. So we call the function as a bijective function. So hope the definition is clear to you, and if an arrow diagram is given to you, you can easily identify whether the given functions are 1, 1, onto or bijective. Now let's move to the problem side. We'll do a few questions and then let's see whether we are able to identify the given function as 1, 1, onto or bijective. So here is the first question. What's the question? Let A be the set of all 50 students of class 12 in a school. Let F be a function from A to N. N stands for set of all natural numbers, 1, 2, 3 it goes. And what is A? A represents 50 students of a school, 50 students of a school in class 12. Now we are going to, and how is the function defined? The function is defined by f of x is equal to roll number of x. Here x represents the student. So and the image f of x is, what is f of x? F of x is a roll number of each student. Show that f is 1, 1 but not onto. So it's given in the question, show that the given function is 1, 1 but not onto. So how can we check whether the given function is 1, 1? Here the function is from A to N. So in A we have 50 students. Okay, 50 students, and then N, it's set of all natural numbers, say 1, 2, 3, it goes. Okay. Suppose I take the first student, maybe a student whose name starts with letter A, and naturally he will get a roll number 1. His roll number will be 1. So, if I take the next student, his roll number will be 2. So, if I follow the alphabetic order, I will get roll numbers for all these 50 students. So, now how can you conclude this is 1 1? If I take a student, will that student have 2 roll numbers? No, that is not possible. So, each student will have a unique roll number. So, I can conclude the given function is 1 1. That is, every student has a unique roll number, not 2 different roll numbers. So, the given function is 1 1. And then how can you show that function is not onto? So, not onto means if you can find a member in the second set that does not have a pre-image, we can conclude it is not onto. So, now second set is set of all natural number. It starts from 1 2, it goes. Now, consider 51. Up to 50, definitely there is a person on the other side, a student with roll number 49 50. Now, if I take 51, 51 is a natural number. Does that have a pre-image? Will there be a student in a class of 50? There are 50 students in a class. So, will there be a student whose roll number is 51? No. So, how can you conclude this? The given function is not onto because 51 does not have a pre-image. Not only 51, all the numbers coming after that 52, 53 does not have a pre-image. So, we proved the given function f of x is equal to roll number of x. It is 1 1. How did we prove 1 1? Because every student has a unique roll number. So, different members goes to distinct members. It is 1 1. And how did we prove that it is not onto? For that, I took a member 51 on the right side, and 51 does not have a pre-image. There is no student whose roll number is 51 and above. So, we proved that the given function is 1 1 but not onto. So, now the next one. Prove that the function f from R to R means set of all real numbers given by f of x is equal to 2x is 1 1 and onto. So, we need to prove it is 1 1 and onto. So, to prove something is true, we will always go for the definition. What was the definition of 1 1 function? F of x1 is equal to f of x2 implies x1 is equal to x2. So, to prove it is not 1 1 or not onto, you just show one example so that it is understood. The rule does not holds for that particular member. So, we will prove it is not 1 1 and onto. But here it is to show the given function is 1 1 and onto. So, let us start 1 1. We will have to take 2 members in the first set. So, let x1 comma x2 belong to R, and which R is that? The first set. So, f of x1 equal to f of x2 implies f of x is 2x. So, what do you mean by f of x1? X is replaced by x1. So, I get 2x1 is equal to 2x2. 2 and 2 get cancelled, which implies x1 is equal to x2. So, we proved the condition of 1 1. F of x1 equal to f of x2 implies x1 equal to x2. Now, how can we prove this function is onto? For that also we go for the definition. What was the definition? We consider a member in the second set. So, let y belong to R. Which R is this? It is a codomain. Okay, let y belong to R, codomain. Then f of x is equal to y implies Now, we are going to check whether there exists an image x in the first set. So, if I consider y in the second set, f of x equal to y implies, what is f of x? It is 2x. I get 2x is equal to y. Now, I am going to separate x and y, which implies x is equal to y by 2. So, I took an element in the second set, I got an x in which set? First set, such that f of x is equal to, now we replace x with this y by 2, f of y by 2 is equal to, now f of x is 2x. So, f of y by 2 is equal to 2 into y by 2. Are we getting y as the answer? Yes. So, we got y as the answer. So, come back to the definition. For every y in the codomain, I got an x. What is that x? Say y by 2, such that f of x is equal to y. So, we proved the given function is onto. So, if you have any doubt, do one thing. The second set is real numbers. Just take any real number, say 1, y is equal to 1. So, what will be the pre-image of 1? Just substitute 1 in the place of y. So, you are getting x is equal to 1 by 2. Now, you give y as 3. So, what will be the pre-image? 3 by 2. Give y as 5. What is the pre-image? 5 by 2. So, for any real number, their x is a pre-image. So, instead of listing one by one, we just gave the general proof. So, the given function is 1, 1 and onto. So, what is the name of that function which satisfies both? We call that function as bijective function, and this is an example for bijective function. So, now let us move to the third question. So, what is given here? Prove that the function f from n to n given by f of x is equal to 2x is 1, 1 but not onto. So, now this question is similar to the second question, but in the second question domain and codomain they are different. There it was r, here it is n, that is natural numbers. So, now let us see how we can prove that this function is 1, 1 but not onto. So, let us start 1, 1. So, what is the definition? F of x1 is equal to f of x2 implies. Now, what is f of x here? It is 2x. So, f of x1 means wherever x is there, we replace that with x1. So, we get 2x1 is equal to 2x2, which implies, now what we can cancel 2 and 2, 2 and 2 get cancelled and we get x1 is equal to x2. So, we proved that the given function is 1, 1. And what was the definition of 1, 1? F of x1 equal to f of x2 implies x1 is equal to x2, and we got that. Now, look at the second part. Prove that this is 1, 1 but not onto. So, to prove something is false, just one example is enough to show that it violates the rule. So, we are going to show that it is not onto, that is we are going to show with the help of an example that the function is not onto. So, now let us consider onto. So, what was the definition? We will consider y in the second set and then we will prove that there exists an x in the first set such that f of x is equal to y if a function is onto. But here the question is prove that it is not onto. So, anyway, let us consider a y in n. Which n is this? It is a codomain. Codomain. Now, f of x is equal to y implies, what is f of x, children? It is 2x equal to y. Now, we are going to separate x and y, which implies x is equal to y by 2. Now, from this step, what are we going to do? I am just giving one example, one value for y, and then I am showing that there does not exist a pre-image for that particular y. For example, suppose let us consider y is equal to 1. 1 is a natural number and this y comes from the second set. Now, when you substitute this y here, what is your x? X is equal to 1 by 2. So, when y is 1, x is equal to 1 by 2. But then where does this x come from? First set. Now, look at the first set, it is set of all natural numbers, but this 1 by 2 does not belong to n. So, what did we prove here? 1 does not have a pre-image. 1 does not have a pre-image in the first set. Now, what is a function? F of x is equal to 2x. That means whatever value x takes, answer is always an even number because it is 2x, isn't it? That means your image will be always an even number. That means odd numbers will never come as the answer. So, this is just a particular case. I gave y as 1, it does not have a pre-image. Same way I can conclude, if I take any odd number, there does not exist a pre-image for that. So, what is the conclusion? We proved the given function is not onto. So, therefore, f is not onto. It is 1, 1. We proved using definition and we just showed one example so that the given function is not onto. Okay, now let us move to the next question. Question number 4. What is it? Show that the function f from R to R, its R is real numbers, defined by f of x is equal to x square is neither 1, 1 nor onto. Okay, it is neither 1, 1 nor onto. So, it is enough to give examples so that we can complete our work. So, what is the function here? It is given f of x is equal to x square. So, now let us start with 1, 1. I am just going to take two members from here. The first set, that is our domain. Two real numbers, say 1 and minus 1. So, what is f of 1? I will substitute 1 here, I get 1 square which is 1. F of minus 1, what is my answer? That is also 1. So, here my x1 is 1, x2 is minus 1 and I got f of x1 is equal to f of x2. Does that mean x1 and x2 are same? But what is x1 here? 1 and minus 1, they are two different numbers. So, that means, but x1 not equal to x2, hence f is not 1, 1. Isn't it? What is it? It is many 1, many going to 1, 1 goes to 1, minus 1 also goes to 1. So, we prove it is not 1, 1. Now, let us take the next part, that is we are going to prove it is not onto. The same method, we will take one example and then we will prove it is not onto. So, coming to onto. Given function is f of x is equal to x square. So, whatever value I give for x, your image, that is the answer is square of that number. So, if I take any real number, that real number when squared gives a positive answer, isn't it? We will not get a negative answer because square of any number is positive. So, whatever value I give for x, answer is positive. Okay? So, now let y belong to R. Which R is this? Codomain. I am just considering a y in the second set. Okay. So, say I will give one example, y is equal to minus 1. Minus 1 is a real number, isn't it? So, can you find an x in the first set so that square of that number gives minus 1? No, you cannot. because we know square of no number gives a negative number, because we are dealing with real numbers. So, what is the conclusion? -1 does not have a pre-image. Okay, that is not the case with -1. All negative numbers, if I consider, they will not have a pre-image. So, we proved the given function is not onto. So, when y is -1, -1 does not have a pre-image. Hence, f is not onto. Okay. So, the proof is over. So, we proved it. Now, coming to the next question. Prove that the greatest integer function f from R to R given by f of x is equal to box x. Box x means greatest integer function. It is neither 1 1 nor onto. Here also we are going to prove it is not 1 1 and it is not onto. So, children, what do you mean by greatest integer function? What is the definition of greatest integer function? If I write greatest integer x, what does that mean? It means the answer will be an integer which does not exceed the value x. For example, if I consider box 0.5, what is the answer? I need an integer which will not exceed 0.5. So, what is the answer? The answer is 0. Greatest integer not exceeding x. Okay. So, now we are going to prove this is not 1 1 and not onto. So, given f of x is equal to greatest integer of x. So, now I am going to take two numbers, say x1 and x2. So, let it be, say, f of 1.1, that is equal to box 1.1. What is the answer, children? It is 1. Greatest integer not exceeding 1.1. Same way I am just considering f of 1.9, and what is that? Greatest integer of 1.9, and what is the answer? It is 1. So, look at this, my x1 and x2, they are different, but the function values are same. Many goes to 1. So, the given function is not 1 1. Therefore, f is not 1 1. Now comes onto part. So, how can we prove this function is not onto? So, children, remember when we discuss onto, like after the definition we said one more condition to prove a function is not onto. What was it? If range of the function is not equal to the codomain, then also we can conclude the function is not onto. So, when we are discussing onto, here function is box function, greatest integer function. What is the range of greatest integer function? Now, range of greatest integer function is equal to, what is the range of greatest integer function? It is z. And what is the set? Set of all integers. So, on the right side, whatever value we give for x, answer is always an integer. Now, what is our codomain? The function is from R to R. So, our codomain is R. So, I can say range not equal to codomain. So, range not equal to the codomain. So, we proved that the given function is not onto. It is neither 1 1 nor onto. Next question. Sixth one. Show that the modulus function f from R to R given by f of x is equal to mod x is neither 1 1 nor onto. So, children, what is the definition of mode function? Mod x is equal to x when x is greater than or equal to 0 minus x when x is less than 0. Meaning, if we give any value for x, answer is always positive. Modulus of 1 is 1, modulus of minus 1 is 1. Okay? So, answer is always positive. So, now how to prove it is neither 1 nor on 2? That is very simple. We will take the first one, that is 1 1. If we can show two numbers goes to the same number, we can prove it is not 1 1. So, now let us consider two numbers, say 1 and minus 1. So, f of 1 is equal to modulus of 1, that is equal to 1. F of minus 1 is equal to modulus of minus 1, that is equal to 1. So, now look at this, many goes to 1. So, the given function, it is not 1 1. Why? Because f of x1 and x2 are same, but x1 not equal to x2. Function value same, but the numbers x1 1 not equal to minus 1. Now, how can we prove it is not on 2? For that, I need to give an example such a way that a number is there in the second set which does not have a pre-image in the first set. So, what example can we give? We all know whatever input value we give for x, the answer is always positive. But look at our codomain is R, and R means it is a mixture of positive numbers and negative numbers. So, consider minus 1 in R. Which R is this? Codomain. Codomain. Modulus of what gives minus 1? No number. So, there does not exist a minus 1 does not have a pre-image. So, this example is enough to prove that the given function is not on 2. And not only minus 1, all negative numbers if I take on the right side, they do not have a pre-image. They do not have a pre-image on the left side. So, we proved the given function is not on 2, or in other words I can say range of the function not equal to codomain. Both are correct. And one more example, a very simple type, show that the signum function f from R to R given by f of x is equal to 1 when x is greater than 0, 0 when x equal to 0, minus 1 when x is less than 0 is neither 1 1 nor on 2. Here also we are going to show examples because it is said prove it is not. So, one example is enough. Now, from here see, for all x greater than 0, what is the image? It is 1. So, if I take 1, that is f of 1, the answer is 1. F of 2, the answer is 1. So, for all numbers greater than 0, the answer is 1. So, I can prove the given function is not 1 1. So, from here I can conclude here f is not 1 1. And how can you prove it is not on 2? What is the range of signum function, children? Range of signum function is only 3 members comes inside the range, either 1, 0 or minus 1. So, and what is our codomain here? Codomain is R. So, is range equal to codomain? No. So, we will conclude this function is not on 2. So, range is equal to set minus 1 0 1, and that is not equal to the codomain. And what is our codomain? R. Because if you take a member, say 2 in the second set, can you find a pre-image for that 2? No, because for all numbers greater than 0, your answer is 1, and for all numbers less than 0, your answer is minus 1, and for 0, the 0 goes to 0. So, 2 will not have a pre-image. Like that, so many members are there which does not have a pre-image. So, we will conclude the given function signum function, it is neither 1 1 nor onto. Coming to the next one. In each of the following cases, state whether the function is 1 1 onto or both. Or both means bijective. So, let us check the, so it is said to check. So, we need to check, we will just go for the definition and then we will prove whether it is 1 1 or onto. So, let us consider the first question. We will prove whether it is 1 1. So, we have the definition, let x1 x2. So, we will just take two members x1 x2 belong to R. So, f of x1 equal to f of x2 implies, what is f of x? 3 minus 4x. So, what is f of x1? 3 minus 4x1. So, 3 minus 4x1 is equal to 3 minus 4x2. 3 and 3 get cancelled, which implies minus 4x1 is equal to minus 4x2. Again I can cancel minus 4 and minus 4. So, we get x1 is equal to x2. So, we proved the given function is 1 1. F of x1 equal to f of x2 implies x1 is equal to x2. Now, let us check whether it is onto. For that, let us consider an element in the second set, y in R, that is a codomain. F of x is equal to y implies, what is f of x? 3 minus 4x is equal to y. Now, we are going to separate x and y. So, when I separate, I get 3 minus y is equal to 4x. Or x is equal to 3 minus y divided by 4. So, for every y in R, I got an x, that is 3 minus y by 4, such that, now let us check whether when we find f of x, are we getting the value y, such that, so what is f of x? F of x is equal to f of 3 minus y by 4. And what is that? In the place of x, I am going to substitute 3 minus y by 4. So, 3 minus 4 into 3 minus y by 4. 4 and 4 get cancelled. Now, let us open the bracket. 3 and minus 3 goes and we got the answer as y. So, what is it? For every y in the second set, you got an x such that f of x is equal to y. So, we proved the given function is 1 1 and onto. Now, let us see whether the second one is 1 1 and onto. So, what is the function given here? F of x is equal to 1 plus x square. F of x is equal to 1 plus x square. So, we will just check the 1 1 condition. Let x1, x2 belong to R. F of x1 equal to f of x2 implies 1 plus x1 square is equal to 1 plus x2 square. 1 and 1 get cancelled, which implies x1 square is equal to x2 square. What does that mean? x1 is equal to plus or minus x2. If you take the root, I get x1 is equal to plus or minus x2. So, x1 is equal, I did not get x1 equal to x2, I got x1 is equal to plus or minus x2. For example, if I give 1, what is f of 1? F of 1 is equal to 2. If I give minus 1 here, what is f of minus 1? You are getting the same answer, 2. So, which implies f is not 1 1. F is not 1 1 because many goes to 1. Now, let us prove the next part, that is onto. As usual, let us consider a member y in the codomain R. So, f of x is equal to y implies 1 plus x square is equal to y. X square is equal to y minus 1. So, what does that mean? X is equal to, we just take the square root, x is plus or minus root of y minus 1. So, we reached here. Okay. So, from this step, I am just giving a y value as 0 and just let me check whether it has a pre-image. Suppose you give y as 0, your x is root of a negative number and that is not a real number. So, from this step I would conclude the given function is not onto, that is when y is some 0, x is not a real number. So, we proved the given function is not onto. Now, we have another one. Show that the function f from n to n given by f of 1 is equal to f of 2 is equal to 1 and f of x is equal to x minus 1 for every x greater than 2 is onto but not 1 1. So, we need to prove that it is onto but it is not 1 1. So, just let us check. Here the first set is n, second set is also n, the function is from n to n. Now, that is 1 2 3, it goes 1 2 3 natural numbers. It said, I will just list 1 2 3 4 members are there. Here also I have 1 2 3 4 5 6 7. Okay. Now, f of 1 is 1. What does that mean? 1 goes to 1. F of 2 is 1. 2 goes to 1. And for x greater than 2, for numbers greater than 2, that is from 3 onwards, it is a different thing. F of x is x minus 1. So, that means if I take 3, 3 goes to 3 minus 1, that is 2. 4 goes to 4 minus 1, 3. 5 goes to 4. 6 goes to 5, like that. So, now how can you prove it is not 1 1? It is very evident because see, f of 1 is 1, 2 is 1. So, 1 and 2 goes to the same member. So, it is many 1. That is, we prove it is not 1 1. So, how can you prove it is not 1 1? F is not 1 1. What is the reason? As 1 and 2 have the same image. Same image. Now, how can you prove it is onto? How do you prove it is onto? We take a y and then we prove their x is a pre-image for that. So, now if your y is 1, then definitely it has a pre-image, 2 pre-images 1 and 2. Okay. So, when we take y, let us take y other than 1. So, to prove onto, let us consider a y which is not equal to 1. Okay, let y not equal to 1, it is greater than 1. Then f of x is equal to y implies x minus 1 equal to y. X is equal to 1 plus y. That means, for any y other than 1, you got an x 1 plus y such that f of x is equal to f of 1 plus y is equal to 1 plus y means in the place of x we give 1 plus y minus 1. So, I get the answer 1. So, if any y you take here, suppose my y is 4, what will be the pre-image? It is 4 plus 1, that is 5, and it is evident from this figure. Suppose I take y as 5. So, what will be x? 1 plus 5, that is 6. So, we proved the given function is not 1 1, but it is onto. Every element in the second set has a pre-image. 1 has pre-image, and for numbers other than 1 also there exists a pre-image, say x is equal to 1 plus that number, 1 plus y. Hope that is also clear. Now, we will do just one more question, that is, show that the function f from n to n given by f of x is equal to x plus 1 if x is odd, x minus 1 if x is even, is both 1 1 and onto. So, we are going to prove it is 1 1 and onto. So, usually when we prove something is true, we take the help of our definition, that is, for some x1 x2, f of x1 is equal to f of x2 implies x1 equal to x2. So, now from where do we select this x1 and x2? From the first set, isn't it? But then here the function is divided into two. For odd numbers it is x plus 1, and for even numbers it is x minus 1. So, when you select x1 and x2, x1 can be odd, x2 can be even, x1 can be even, x2 can be odd, or both can be even, both can be odd. So, how can you select x1 and x2? So, let us just assume, just consider, let us consider x1 is odd and x2 is even. So, f of x1 equal to f of x2 implies odd means where will you substitute here? I get x1 plus 1 is equal to, when x2 is even I go to this. So, I get x2 minus 1. So, if you shift there, if you shift x1 and if you bring 1 there, we get x2 minus x1 is equal to 2. That is not true. Okay, x2 is an even number minus odd number 2. No, that we need to get the condition x1 equal to x2. So, this selection of x1 and x2 is wrong. Same way, if I interchange, that is, if I interchange x1 as an even number, x2 as an odd number, still you will see that the condition will not hold. We can verify it. So, how should we choose x1 and x2? If you are choosing x1 and x2, x1 and x2 it should be both odd, or x1 and x2 should be both even. Now, let us check, like if I take the second case, that if I take x1 as even and x2 as odd, f of x1 equal to f of x2 implies even means here x1 minus 1 is equal to f of x2, x2 is odd. So, I substitute x2 in the first slot. So, x2 plus 1. So, what do I get, which implies x1 minus x2 is equal to 2. So, that also does not gives us the answer x1 is equal to x2. So, these type of selection, it is wrong. So, how should we select? We need to select in such a way that x1 and x2 are both odd or both even. So, let us select like that. So, we are going to prove the 1 1 condition. Let x1 and x2 be both odd. So, f of x1 equal to f of x2 implies both are odd means we just check this one. x1 plus 1 is equal to x2 plus 1. 1 and 1 get cancelled, which implies x1 equal to x2. So, what does this mean? x1 and x2 are both odd. So, we proved the given function is 1 1. That means odd numbers, different odd numbers goes to different members on the right side. So now here we took x1 and x2 as odd. So let x1, x2 be both even number. So f of x1 equal to f of x2 implies, so if both are even, so we will substitute here. So that is x1 minus 1 is equal to x2 minus 1, which implies x1 is equal to x2. So our selection was right, we got it is 1 1. So when x1, x2, when I took that both of them are odd, I got 1 1 condition. When x1 and x2 is even also, I got the condition f of x1 equal to f of x2 implies x1 equals x2. So we prove it is 1 1. Now let us see how we can prove it is onto. So here the function is from n to n. N to n. You have 1, 2, 3, 4, 5, 6 natural numbers. Here also we have natural numbers. And see, if x is odd, your answer is x plus 1. So look at this 1. 1 is odd. So 1 goes to x plus 1, that is 1 goes to 2. Now next odd number I took 3. 3 goes to 4. 5 goes to 6. So that it goes. Now what is the case for even numbers? When x is even, your image will be x minus 1. So here you have 2. 2 is an even number. So 2 goes to 1. 1 number less than that. Now 4 goes to 1 number less than that, that is 3. And 6 goes to 5. So this is a procedure. So now how can you generalize this? Look at this side. If I take separately, odd numbers separately, so 1 is going to 2, 3 goes to 4 and 5 goes to 6. All odds are going to even numbers. So that means if I take a general even number 2r on the right side, what will be the pre-image of that? 2r, if it is 6, it is 5. That means one number less than that. So 4 means it is 3. So in general, if I take 2r on the right side, its pre-image will be some 2r minus 1, such that f of 2r minus 1 is equal to 2r is even, so 2r minus 1 is odd. If something is odd, what is the answer? It is x plus 1. So I get 2r minus 1 plus 1. What is the answer? 2r. So that means for every even, there is an odd such that there is an odd pre-image, and that is a conclusion. Now same way we will check the nature of evens going to odd. That is, here we have 2 going to 1, you have 4 going to 3 and you have 6 going to 5. So on the right side you have an odd number. So for some odd number, say I will just consider 2r plus 1, I can find a pre-image. The pre-image of 5 is 6, that is 1 greater than that. 3 is 4, 1 greater than that. So I can say there is a pre-image 2r plus 2 such that f of 2r plus 2 is equal to. Now 2r plus 2 is even. When something is even, it is x minus 1. So I will substitute there 2r plus 2 minus 1, and what do you get? You get 2r plus 1. So by taking two cases, we proved for every y in the second set, there exists an x in the first set such that f of x is equal to y. So we did 10 questions based on this topic. Hope this topic is clear to all of you. So let's wind up today's session. Thank you.